Our final speaker today is Robert Wang. Robert received his Bachelor of Science in Electrical Engineering from the University of Massachusetts Amherst and completed his Master's in Engineering in Power Systems from Worcester Polytech Institute. Starting with OMICRON Electronics in 2011, Robert serves as product manager focusing on recloser control testing and applications. He has a particular interest and focus on the subjects of distribution automation and power system reliability. He is also a member of IEEE Power and Energy Society. Please join me in giving a warm virtual welcome to Robert Wang. Robert, we'll now pass the control presenter rights to you.
Thank you, Wang. Can everyone hear me okay? Great.
Yes. Yep.
So thank you again, everyone, for participating in our webinar. I know it's a very difficult time for everyone. And my presentation today is going to be about a new method of testing distribution automation schemes. The first thing I really want to talk about are the investments going into distribution automation. In the US alone, including the IOUs, public power providers, and co-ops, utilities have invested over $155 billion in electric generation, transmission, and distribution infrastructure in 2017 alone. This data has been gathered from EEI, and 2017, unfortunately, is the latest data that's available. So from here, we can see that major IOUs alone, which serve about, I would say, 73% of the US electricity customers, spend about $50 billion on T&D that delivers electricity to customers. 22 billion of that is for transmission, about a little over 28 billion is for the distribution grid. Distribution infrastructure investments often cycle as equipment wears out and gets old and is replaced. And this chart shows that distribution investments by IOUs have grown incrementally in the last 2 decades, reaching a high of over 28 billion by 2017. Of this 28 billion, the largest investments were into either poles and fixtures, overhead conductors, station equipment to not only replace, but also upgrade and harden the system against outages from the growing frequency of, extreme and high-cost weather events, whether it be from hurricanes, fires, or storms and floods. So, of that $28 billion, according to Bloomberg New Energy Finance, the U.S. utilities invested in 2016 an estimated about $3.4 billion in just smart grid technologies alone, and this is for the distribution level. And about 13% of that allocated money was spent on distribution infrastructure by only the large IOUs. So if you take a look at this graph, since 2008, U.S. utilities have invested about $31.6 billion, so this is from 2008 to 2016, on distribution level smart grid technologies, which was much higher than what was originally predicted. So if we just take a look at 2006 alone and the investments made that year, we see about $1.5 billion being invested into smart metering, which we see in blue. So this includes, smart meters and related communications, as well as IT infrastructure. In red, this represents advanced smart grid applications that go beyond regular distribution automation. So this might include something like active network management, integration of distributed generation, maybe load control, home energy management, and electric vehicle charging. And lastly, in yellow here, we see that these are the investments made into distribution automation. So since 2008, we've seen a 183% increase of investments into DA technologies. This can include, feeder and substation automation, distribution management, volt VAR optimization, CVR, as well as Blizzard. According to a 2019 Newton Evans report, they polled a bunch of the U.S. utilities and asked them questions with regards to their distribution automation, how much they're spending, what they're spending it on. And these are some of the questions that they brought up. They asked approximately what percentage of all your feeders have or will have FLISR or FDIR. Overall, the survey respondents indicated that on an average of 11% of the feeders in the current sample size have FLISR, while an additional 8% will have FLISR by the end of 2020. IOUs reported that 20% of their feeders have FLISR, with an additional 12% being upgraded by 2020. And larger IOUs, so this is with typically customers of $500,000 and more, reported that 25% of their feeders currently have FLISR. An additional 17% on top of that will have FLISR by 2020. Next, they asked, if possible, please approximate the percentage of the DA budget that applies to purely FLISR technologies. So on average, 59% of the funds indicated that all utilities surveyed go to FLISR. IOUs indicated as much as 72% of their budget, of their GA budget, is allocated for FLISR. And a subsample of the larger IOUs surveying, again, over 500,000 customers indicated as much as 77% of their budget would go to FLISR. Sorry, I forgot to advance the slide. Here's that data here. So why do utilities want to spend all this money on distribution automation and implementing these FLISR schemes? So as mentioned by the utility presenters earlier today, of course, increasing reliability, service quality, those reliability indices where if they don't meet certain numbers, they can be penalized. They want to reduce their costs in terms of the crew that they might have to go out to send to do some switching operations. It gives them an opportunity to justify increased billing as well as provide improved customer service. So at the end of the day, it all comes down to money. So before we move forward to talking more about FLISR, I want to give everyone a quick FLISR update. So in case you've forgotten or maybe are not too familiar with the term, let's just go over a brief example of a scheme. So this is an example of a communication-based FLISR scheme. All of the squares are 1 through R5, and you can extrapolate that as much as you want. These represent reclosers, and the light bulbs indicate customers that are being fed off of these taps. So if we have, let's say, a fault occurring between R3 and R4, of course, R1, R2, R3 will all detect this fault. What will happen is, because R3 is the closest recloser to the fault, it will send a blocking command subsequently to R2 and then subsequently to R1. Once recloser 3 trips and opens, we see that the customers beyond that will be out of service. The normally open tie recloser will then be issued a command to close, therefore restoring customer service to the customers between reclosers 4 and 5. So when we implement such complicated schemes, such as Amar had mentioned, and I believe Kelly has also mentioned, we need to perform some testing. Oftentimes, these utilities that put these into operation rely on either manufacturers to design and implement the automation scheme, and through testing of the entire scheme thoroughly prior to installation, we know that it's critical to make sure that the switching logic works as desired for a multitude of various fault scenarios that may occur in the network and affect the network, as well as the communication equipment that can support the resulting network traffic. The testing process is integral for the verification of the system, but can also be very complex, labor-intensive, as well as time-consuming. So that begs the question, how do we go about testing, right? If it's so complex, how is it done in the world? So when testing a GA scheme with communication or distributed logic, Test needs to include all the protection devices in the scheme in order to verify their correct functionality. A DA scheme can be implemented with, hundreds to thousands of lines of custom code or custom logic for both the Recloser control itself as well as any kind of, automation controller. So prior to a scheme being deployed in the field, it needs to be thoroughly tested to ensure that a scheme operates as expected, especially if it's put into operation. When the fault occurs, the DA scheme needs to identify, locate the fault, and to figure out the best way to clear the fault and restore the unfaulted line segments through, various switching sequences. These switching sequences also need to be tested to fully verify the functionality of the scheme. So let's talk about briefly the conventional method of testing these DA schemes. Typically, these are only done in the lab, and for a lab test of a DA scheme, all devices are set up in a lab environment. These tests are typically performed as a proof of concept for a new project or acceptance testing of a scheme prior to installation in the field. This is done usually using secondary injection test devices connected to each Recloser control with various pre-programmed test sequences that can be executed to test the logic and communication, which are essential to the scheme. Scheme testing can be extremely complex and may require, weeks to months. For every type of fault scenario, load and fault values for each operating state must be calculated for every single Recloser in the scheme in order to simulate realistic faults. Then for the execution of each test case, local coordination to turn on test injection or, IRIG-B signal or any kind of coordination for specific designated times is needed to simulate each step of the test case, which is required. Any kind of mistake or miscommunication amongst any of the test personnel would then result in an inaccurate test. Then, after execution, the results from each of the locations must be collected, merged, and assessed, matching up all the different timestamps. Then, after all this is done, any issues are discovered, the automation logic would need to be adapted in order to address any of the problems. So some of the disadvantages of the conventional testing method. So as previously described, the method that we talked about, the conventional method, has proven to work well in labs. However, it comes with some disadvantages. The expected test values need to be calculated and programmed into a sequence for every single test device, which can be a very time-consuming process. Tests under real-life conditions require the test values to match those of real-life faults as closely as possible. The method of testing that we described here uses static fault values, which are typically applied, and then the resulting reaction from the Recloser is measured. Under realistic cases, a DC offset is typically present, and depending on the algorithms of each Recloser control, one device in the scheme might detect the fault faster than another. So in order to determine the real performance of the scheme, it's always beneficial to test with transient signals. We found that introducing additional components into the test setup, this not only increases the complexity of the test, but also increases the chances that PC software versions, firmware versions might not be compatible with local hardware. So with any kind of increase of assets, you're always going to run into a problem where you might have an increase of issues with compatibility. Another issue could be that the coordination between test engineers and technicians of when to begin the test can be very troublesome, and it can provide technical issues. And then lastly, after the test, additional time must be spent comparing timestamps from each of the test results from each of the test devices, matching them up, and then making sure that they all align accordingly. So beside all of these disadvantages which I described, there's some additional factors which can influence the performance or even basic function of a scheme which we have not yet considered. So when a DA scheme is installed in the field, the distances between each and individual Recloser can be much farther than when they're in the lab. So these longer communication distances can provide, it's possible that they could be weak communication links between them and waveforms of faults that are different from those that are static. Fault values can be drastically affect the operation of the testing of the scheme. So now we must ask the question, how can we make this easier for ourselves, right? Is there a button that we can press that, like the old Staples commercial, I want to make it easy? So for this, I'm going to propose the idea of a system testing approach, where we approach testing the GA scheme or the Flizzr scheme as a black box, where we only have to know very basic settings of the system, of the specific reclosers, and we don't need to know the internal workings so much of the scheme. So what we're doing is we're basically applying some inputs and some stimulus to the system, and we're seeing how it reacts. So this can typically only be performed during, acceptance testing and commissioning, and it's not very common for maintenance testing. Now, imagine this new method where a power system under test can be modeled in a single line diagram editor, and devices such as reclosers, circuit breakers can be placed within the network. In-feeds can be defined by entering various source information like the source impedance ratio. All the line data can be calculated by using line length and entering the line impedances. And loads in the network can be specified using active and reactive power data, which should be already available to you. Using all these data points, a software can calculate the resulting load and fault values for any kind of user-defined test case. The behavior of each circuit breaker or recloser should be defined within this simulation software. If a breaker or recloser opening and closing times are known, or have been previously measured using any kind of breaker timing device, the software can allow for the input of these times, which are taken into consideration to ensure the most realistic kind of test. Using any kind of modern secondary injection test set, these typically have built-in circuit breaker simulations, which can be extremely beneficial for this type of testing. And using any kind of binary output to these types of test devices, any kind of 52A or 52B contacts can also be simulated. And it does not require the circuit breaker or the recloser to be connected during such a test. Now, in this new method, we should also try to eliminate as many of the complexities as possible, right? So our idea is to test all devices from a single PC. So this would require some kind of connection to the remote devices. If a GA scheme is operating with, let's say, goose messaging, and there's an Ethernet connection available between all the devices under test, which could be used to control all the test sets, right? So this is the example on the left, option 1. For this, the test set on site then needs to be plugged into any kind of Ethernet port switch of the controller housing. If this is not available, however, due to either maybe IT restrictions, the test set has to be connected to individual laptops with internet connection, maybe via cloud, or maybe you can tether it with the phone to connect to a cloud. And these services are already available through, Microsoft or Amazon or any of these cloud computing services. So once we establish some kind of synchronization, whether it be GPS, IRB, whatever it is, the test set or the test cases can then be executed. The software can then calculate the resulting fault values for each device at each location. If this test if this test is now executed, the testing software should be able to upload all the test values into all of the test sets simultaneously via the GPS synchronization at the remote end. And once they download all the test procedures, the test sets can then all start synchronously. After all the testing is done, all of the remote devices that are out there should then be able to compile all the results, upload it all the way back to the controlling PC where the results can be compiled and analyzed. So the next question I'm sure on a lot of your minds is, does this method really work? Is there such a case for this? And the answer is yes. So we actually performed such a test case for a highly visible pilot project for a GA at a major East Coast utility, some of which are attending this meeting right now, this webinar, should I say. So the goal of this project was not only to modernize their system by migrating old and outdated overhead infrastructure underground, but to evaluate the implementation of a highly reliable automated switching solution. Previously, for them, if a primary event occurred, all the customers in their radial circuit would be interrupted. And in order to restore any kind of customer outage, local technicians would have to be deployed in order to perform manual switching at the affected locations. This would be both very time-consuming, costly, and potentially dangerous for the local technicians. As you can see from the scheme, it consisted of 9 separate locations, each with their own switchgear, and implemented within each were about 2 multifunctional relays, 1 on each primary switch and 1 on each load tap switch, and a variety of different communication equipment was also used. For the initial testing, so for this, typical testing is usually performed, 1 relay at a time, where you verify each relay is working. You can test all of its protection elements, and this is very standard nowadays, right? It's usually done through element testing. So even though in this scheme it utilized fairly simple protection elements, there's a lot of added complexity when it came to testing because of the communication assisted logic. So this logic required much more attention to detail in testing, which is often difficult to perform via the traditional methods which we mentioned. So in order to test the logic using traditional methods, a tester would have to be able to simulate the adjacent relays in order to mimic their communication just to satisfy the internal logic states. Based on a, I think, 2017 NERC study, while each relay as a component would have been thoroughly tested, very often the interface and components is the cause of most misoperations. So in this system test, errors in communication engineering could not be uncovered with any kind of single relay testing because of the communication between the different relays and their response being necessary. Therefore, to lower the complexity and improve their test coverage, we implemented this new system-based approach. For the factory acceptance test, or the lab test, we are fortunate enough of the manufacturer of the switching solution to invite us into the facility to perform the testing. We see here that we have multiple test sets set up, as well as all of the relays that would be used for the installation. This entire process for us took about 3 weeks, from setting up all the equipment, performing all of the testing, testing all of the test equipment, testing all of the individual elements, and then as well as the final customer witnessing of the testing. So fortunate for us, prior to arrival, all of the protection and testing elements was completed, and they were all tested in order to check for any kind of relay failures themselves. So the time that we spent in the lab was purely based to verify the protection scheme and the communication logic. Next, we can move on to the field test. So for the field test, we implemented 10 different test sets to simulate all the primary pathways for all 9 of the underground bolts, as well as 1 of the individual load tapways. The testing techniques utilized, centralized testing software, which was used to simulate the power system disturbances and distribute testing programs to all of the different test devices that were installed out in the field. The test set would then, send all of the start times to all of the remote locations, and after all the tests were completed, would compile all of the test data for processing and analysis. So one of the major hurdles which presented itself, so it's an issue that we actually found with the system that we would not have otherwise found using the traditional testing method or just individual relay testing, was the difference of topology between the first lab test versus the site test, where it was actually installed. So due to the physical limitations of some of the rooms where each of the switching devices was housed, the directionality of some of the switches had to be reversed. So we see that in the cases of, they refer to them as vaults, vault 1, 2, 4, 5, and 6. So the orientation of them sometimes would be switched, and then the relays would then also be installed where they were switched. So electrically speaking, I don't think this really presents that big of a problem for the switchgear to handle, as the switchgear bus operates purely as a node. However, this did present a problem with the communication-assisted protection with respect to the communication scheme, the fiber communication scheme. The virtual bits had been mapped in such a way, with a specific directionality in mind, and these had to be reworked for the entire process. So without this method of testing, there would be no way for us to really verify that this had been installed incorrectly until an actual event had occurred and the inappropriate switching, if this had been turned on, had occurred. So in conclusion, this new type of testing can be used in any kind of DA scheme to test both not only the switching logic, but also the communication equipment. The quick assessment, so in terms of compiling all of the data, making sure everything is working from our black box approach where we apply inputs, see the outputs, we can quickly verify to say, yes, the correct switching operations did occur, did not occur. And these tests can also be not only be used in the lab, but also be replicated out in the field via the GPS synchronization of remote test sets. As mentioned previously, the steady state signals that are typically used, we can now use transient signals to ensure a realistic faults. And from that, all of that combined, we can make sure that the scheme, the performance of the scheme is correct, and we can give it a thumbs up before putting it into operation. With that, I think I can take some questions.
Okay, Robert, thank you very much for that presentation. Much appreciated. We can now, pass the mic over to Eugenio and see if there are any questions from the audience. Eugenio?
Thank you, Wayne. Thank you, Robert, for the presentation. Looking at the questions, so the first one is related to one of the slides that you showed. And the question is, when testing a scheme in the field using the cloud application, does the latency of the cloud affect the testing of the scheme?
It should not, because all we're using the cloud to do is to send all of the test requirements to all of the individual test sets, and then based on the GPS coordination, they can start all of the tests at the same time. So once all the tests are started, it injects, it gets the feedback from the system, or each individual recloser holds the data and then sends the data back through the cloud. So that shouldn't add any additional latency to any kind of, scheme operation, only to maybe the duration of the test.
Thank you, Robert. I think we have time for one more. And this is also something we discussed during the presentation from ComEd and Emcee about the different schemes for the freezer, like centralized or decentralized. So the question is, does this test approach apply regardless of the protection scheme used?
Yeah, I would say that you can use this for testing any type of automation scheme, no matter what kind of automation is used.
Okay, thank you, Robert. Wayne, then back to you.
Okay, thank you very much, Eugenio, and thank you, Robert, for that great presentation.